Have you ever stopped to think about how your smart devices, well, how they know things? It's pretty amazing. They're constantly translating the world around us, things like heat, light, pressure, into this invisible language that computers can actually get their heads around. So today, let's dive into that hidden conversation, the one that basically powers our entire modern world.
It really all starts with a simple question, right? Something just like this. How does my thermostat know it's time to kick on the AC? It feels like magic, but it's not. It's actually this really elegant logical process. And by the end of this, I promise you're going to see exactly how it works, from feeling the heat to making that final call. And here's the really cool part. Every single smart device, and I mean every one, from that thermostat on your wall to the incredibly complex systems running in your car, they all follow the exact same fundamental blueprint. It's a universal four-step journey to turn a physical feeling into a hard digital fact.
So, what is this universal journey? Well, it breaks down into these four key steps. First, we figure out the thing we actually want to measure. Then, we use a sensor to translate it. After that, we clean up that translation. And finally, we turn it into data that's actually useful. Let's walk through each one using our trusty thermostat as a guide.
Okay, first up, the measurand. Now, this is just a fancy technical term for the thing you care about. That's it. It's the specific physical property you're trying to put a number on. For our smart thermostat, the measurand is super simple. It's just the temperature of the air in the room. Next up, we need a sensor. And you should really think of the sensor as a translator. It's the bridge. It takes that physical property, in our case, the heat in the room, and it converts it into a language that electronics can speak. Here, a little device called a thermistor changes its electrical resistance as the temperature goes up or down. It's our link between the physical world and the electrical one. Now, the raw signal you get from a sensor, it's often really, really weak and kind of noisy. It's like a faint whisper in a super crowded, loud room. That's where signal conditioning comes in. This is the process that cleans everything up. It filters out all that background noise, and it amplifies that whisper into a clear, strong voice that the rest of the system can actually understand. And that brings us to the final step, data acquisition, or just DAC for short. Honestly, this is where the magic really seems to happen. This is the stage that takes that nice, clean, amplified electrical signal and converts it into a digital number, a series of zeros and ones that the thermostat's little computer brain can finally process and use to make a decision. So, we've got our number. We're done, right? Not so fast. Is it a good number? Can we actually trust it? See, just getting data isn't enough. We have to follow some really crucial rules to know if our measurements are reliable. Because, let me tell you, not all data is created equal. Let's start with two of the most important concepts, and honestly, two that get mixed up all the time: accuracy and precision. Accuracy is pretty straightforward. How close are you to the real, true answer? Precision, on the other hand, is all about consistency. How repeatable are your measurements? And here's the absolute key. You can be incredibly precise, getting the exact same result over and over and over again, while being completely and totally wrong. That is a dangerous, dangerous combo. And this target analogy just lays it out perfectly. The top row, that's the dream, right? High accuracy, high precision. You are nailing the bullseye every single time. But look at that second row. This is the precisely wrong scenario. All your shots are clustered tightly together, super consistent, but they're nowhere near the target. This one is often the most dangerous because that consistency can fool you into thinking your data is great when it's not. Next up is resolution. And the best way to think about this is just the level of detail. It's the smallest possible change that the system can even notice. It's really the difference between looking at a blurry, pixelated image versus a sharp, crystal clear, high-definition one. The more detail you have, the clearer the picture of what's actually going on. And believe me, this detail matters a lot. A really basic system might only be able to see temperature changes in whole degrees, but a system with higher resolution, it can see changes of a tenth or maybe even a hundredth of a degree. To put some real numbers on it, just moving from a standard 8-bit to a 12-bit system gives you 16 times more detail. That is a massive leap in sensitivity that allows for way smarter, finer control. All right, two other quick but really crucial rules. First is range. This is just about making sure the tool fits the job. I mean, you wouldn't use a regular room thermometer to check the temperature of a pizza oven, right? Second is linearity, which basically just means the sensor behaves predictably. So for every 1 degree the temperature goes up, the electrical signal changes by a consistent, predictable amount. Without that, all our data just becomes garbage. Okay, so we've followed the rules, we've got good, clean, trustworthy data. Now for the payoff. How does our smart thermostat actually use this data to do something to make a decision? And this all brings us right back to that data acquisition system, the DAC. It really is the brain of the whole operation. It's the part that takes us from just having a clean number to taking a final decisive action. So here's the final logic loop in all its glory. The thermostat's processor reads that digital value from its converter. Then it does a quick bit of math to turn that number back into a real-world temperature, let's say 25 degrees Celsius. Next, it compares that temperature to the threshold that you set, maybe 24 degrees. And if it's higher, boom, it makes the decision, turn on the air conditioning. It's simple, it's logical, and it's all powered by good measurement. Now, here's where it gets really mind-blowing. This simple blueprint, measure, condition, acquire, decide, it's not just for thermostats. This is the invisible engine that is powering nearly every single piece of modern technology. So let's zoom out and just see how widespread this really is. I mean, just take healthcare, where these principles are literally saving lives every single day. That little pulse oximeter they clip on your finger, the ECG machine monitoring a patient's heart, they are all following this exact same blueprint, turning physical signs from the body into data that doctors use to make absolutely critical decisions. It's also completely changing how we grow our food. You've got sensors in the soil measuring moisture so we only use water when we absolutely need to. You've got sensors on drones that can check on crop health from high up in the sky. It's all about giving farmers the data they need to be more productive and, more sustainable. And you are surrounded by this system every single time you drive. Your car is basically a rolling network of sensors. They're measuring oxygen to make your engine more fuel efficient, checking tire pressure to keep you safe, and sensing that sudden stop that tells an airbag exactly when it needs to deploy to save your life. And really, at the end of the day, it all comes down to this. This isn't some abstract academic exercise. In so many fields, medicine, aviation, manufacturing, getting the measurement right is everything. Poor measurements, they don't just lead to mistakes. They can lead to disastrously wrong decisions. So, the next time your phone automatically adjusts its screen brightness or you feel your car's anti-lock brakes kick in, just take a second. Think about that invisible conversation that's happening right behind the scenes. What unseen measurements are quietly, reliably shaping your world right this very moment?